AB Calculus, section 5.3, page 2. And we're continuing with the examples from page 1. I have this information up here, this initial information, value of those integrals from page 1, so you can see that as we work through these problems. This first one, we notice that the bounds are backwards, so we can flip those bounds around. Then the value of the integral is the opposite of what it was, so opposite of the integral from 1 to 9 of f of x dx, and that is the opposite of -1 or 1. Looking at this next one, the integral from 1 to 7 of f of x dx, and we look at this given information, we do not have a value for the integral of 1 to 7 of f of x dx, but what we could do is find this integral, the area underneath f of x from 1 till 9, and then subtract off the piece from 7 to 9. So look at what this says. The area underneath f of x from 1 to 9 minus the area underneath f of x from 7 to 9. That will leave us with the area from 1 to 7. This piece was -1 minus a 5, so that answer there is -6. And looking at number 7, the first thing we notice is that the bounds are reversed, so let's flip those around right off the bat. And this is the integral then from 7 to 9 of h of x minus f of x dx. And now separating, opposite of the integral from 7 to 9 of h of x dx plus the integral from 7 to 9 of f of x dx, plus here, because this minus sign that's out here distributes through to this one, so that turns positive. So we have -4 plus a 5, which gives us 1. All right. Looking at a different example, different numbers here, I've given you the value of an integral from -3 to 5 of x squared dx is 152 over 3. The integral from -3 to 5 of x dx is 8, and I want you to find the value of this integral. We have a product here, 2x plus 3 times x minus 1. There is no product rule for integrals. So we are in a bit of a quandary until we remember our algebra and realize we can multiply those two together. And we will get the integral from -3 to 5 of 2x squared minus a 2x plus a 3x, that's plus an x, minus a 3, all of that dx. Now separate, just like we did in the last several examples. We have the integral from -3 to 5 of this 2x squared, but I'm going to pull the 2 out front, plus the integral from -3 to 5 of an x dx, minus the integral from -3 to 5 of 3 dx. Substituting in some information, this is 2. Oh, this integral was 152 over 3, plus this integral was given to us as 8, minus this integral was not given to us, but you should recognize that this is the integral of a constant, which is that constant times the length of the interval. And simplifying, we have 304 over 3 plus an 8 minus a 24. And coming up here, flipping that 304 over 3 into a mixed number that is 101 1/3 minus 16, which is 85 1/3. All right, a few more properties to look through. We have this one, if f of x is greater than g of x for all x within some interval a to b. So let's put some f of x up here and some g of x. And right now, f of x is not always greater than g of x, but if we put some interval here, we put a here and b here, now we see that f of x is greater than g of x within that interval a to b. And looking at this then, we can say that the integral from a to b of f of x dx is greater than the integral from a to b of g of x dx. This is like one of those theorems that you used to get in geometry, something like perpendicular lines form right angles. And you look at it and go, yeah, so? Well, this is one of those things as well. If f of x is larger than g of x, then clearly the area underneath f of x is larger than the area that's underneath g of x. This last property, not a difficult concept, but there's a lot going on in here, and once we put a visual to it, it will be pretty clear. So let's let capital M be the maximum value of a function on a to b, and little m is the minimum value of the function on a to b. All right, so let's just get this much information up here. Here's some function, f of x, and let's set up some interval from a to b. All right, now, capital M is the maximum value of that function. So I'm going to take this height right here and pull that over here. That's capital M. The minimum value here, little m. All right, let's take this little minimum value here and let's extend that all the way across this interval. And let's look at this rectangle that we made right down here. The height of that rectangle is little m. The width of that rectangle is b minus a. So the area of that little rectangle is m times b minus a. All right, how does the area of that little rectangle compare to the area underneath f of x? Clearly it's smaller, which means that the area of the little rectangle is less than the integral from a to b of f of x dx. That's the area underneath the curve. Okay, now go back to this diagram and let's extend a, that vertical, all the way up to big M. And this B, let's extend that up and also extend this height of big M over there. And let's look at now this big rectangle. And the area of that big rectangle is clearly bigger than the area underneath that curve. The height of that big rectangle is big M. The width is some b minus a, and that is larger than the area underneath that curve. So, if we know a maximum value and a minimum value, we can find the area of the little rectangle, find the area of the big rectangle, and then we know the area underneath that function, or the integral of that function, is between those two values. We will do an example for this problem, or for this theorem, on page 3.